pleasure to now introduce Professor Ed Witten, who's going to be talking about fermions and topological phases.
Thank you. So, first of all, it's nice to see all of you here at PSSCMP and PITP. And I'll try to, I'll be lecturing on a topic that's not that distant from what you've been hearing about from Charlie. Mostly about phases of matter that can be understood in terms of non-interacting electrons and topological band theory. I think I'll have to give you all another half a minute to sit down. So I'll be covering topics somewhat similar to what you've been hearing about from Charlie Kane. And I hope there will be some value added in my explanations, but I can't make any promises there. I also will say a little bit about the fractional quantum Hall effect in the second and third lectures. So we'll start by asking under what conditions we should expect to find a relativistic dispersion relation for electrons in a crystal. So in one dimension, the answer to this question is very well known. So I write epsilon of p for the single particle energy epsilon as a function of momentum p. And generically, it's a completely random curve that crosses the Fermi energy somewhere. And there's no reason for the slope to be 0 when the two curves cross. So generically, the slope isn't 0. And then if we linearize the dispersion relation near the crossing point, the energy is a constant, plus a linear term times p minus p0, plus higher order terms that aren't important near the Fermi surface. And then, writing the group velocity v as d epsilon dp, we see that we can have a relativistic dispersion relation analogous to the relativistic dispersion relation for a massless particle in one dimension, with the speed of light c replaced by v. So, v could have either sign. I've drawn the case where d epsilon dp is positive, but the sign of v determines whether the gapless mode that lives near p0 travels to the right or to the left. Now we could make a corresponding continuum model describing that modes near p equals p0. So the continuum model for a one-component massless electron would be a Hamiltonian, which is just psi star times p, but p is minus id by dx times psi. So that would be the standard Hamiltonian for a one-component massless electron in one dimension. So this, I wrote actually, but I meant Hamiltonian. This is a relativistic Hamiltonian for a one-dimensional chiral fermion, except that relativistically the velocity would be the speed of light. And also, minus id by dx is p relativistically, but it's p minus p0 in the condensed matter system. Also, I've omitted from H a constant energy per particle, which was that each particle near the crossing at p equals p0 had a constant energy epsilon of p0. So the condensed matter Hamiltonian would also have, in its energy near the Fermi surface, a constant times the particle number. Now, this one-dimensional example also gives an elementary example of how global conditions in topology constrain the possible low-energy field theory that we can get, and how these constraints then often mirror what is understood in relativistic field theory from the point of view of anomalies. So we have to remember that in the context of a crystal, the momentum p is a periodic variable. And because it is periodic, it follows that every time epsilon of p crosses the Fermi energy from below, as it does here, there's another time that it crosses it from above, as over here. So actually, there are equally many gapless left-moving and right-moving modes. The epsilon dp is positive here, which corresponds to a mode that will travel to the right. It's negative here that corresponds to a mode that will travel to the left. And an elementary topological fact is that a periodic function, epsilon of p, will intersect the Fermi level as many times going up as going down. So there will be equally many right-moving and left-moving modes. In relativistic terminology, the right-moving and left-moving modes are said to have positive and negative chirality. The motivation for this terminology is the following. Here I've written the massless two-dimensional Dirac equation. So it's defined using Dirac's gamma matrices. Eta mu nu is the space-time metric. So, in case you can see the blackboard, eta mu nu is a diagonal matrix with a 1 and a -1 for the time and space directions. And there are two gamma matrices which can be given a 2-by-2 representation. Now, for condensed matter, we would like to write usually, please don't. I'm finished with the blackboard. No. I'll thank you. So, I apologize for writing something invisible, but that was poor judgment on my part. Thanks for turning on the light. So, usually, well, Dirac himself wrote the Dirac equation in Hamiltonian language, and certainly to compare it with condensed matter, we would like to do that. So to write it in relativistic language, first of all, we get rid of the gamma 0 over here by multiplying by gamma 0 and using the fact that gamma 0 squared is 1. That'll move the gamma 0 onto the d by dx term. And then we would like to multiply the whole equation by I, so the left-hand side will be I d by dt of psi, and then the right-hand side should be the Hamiltonian. So we move the d by dx term to the right-hand side, move the gamma 0 over and multiply by I, and we get the Dirac equation in Hamiltonian form. And the Hamiltonian is minus I gamma bar d by dx, where gamma bar is the product of the two gamma matrices. And it's usually called the chirality operator. In 3 + 1 dimensions, its analog, which we'll get to later, is usually called gamma 5. I didn't want to call it gamma 2, as I thought that would be too confusing. So I wrote gamma bar. And it's a 2-by-2 matrix whose square is 1. So actually, you can pick for it a one-dimensional representation where it just equals 1 or -1. And that would give a mode that travels to the right or to the left. So the Fermion state, that's an eigenstate of gamma bar with eigenvalue 1 or -1, is like a right-moving or left-moving one-component fermion. So a more realistic model, Hamiltonian, for the gapless charged modes, allowing for the fact that there are going to be both right-moving and left-moving modes, will be some constant v plus, the right-moving velocity, times a one-component Hamiltonian, with a plus sign times minus I d by dx. But there will also be, with the minus sign, some other constant v minus times a similar Hamiltonian, and the minus sign means that this describes a mode that moves to the left. So relativistically, they would both travel at the speed of light. In a solid, they will travel, or in a condensed matter system, they will travel at different velocities in general. If one's familiar with quantum gauge theories and anomalies, one will recognize that this topological fact, that there are equally many right-moving and left-moving modes, has saved us from trouble. This fact is a one-dimensional analog of a three-dimensional result that we will get to presently. It saved us from trouble because a purely two-dimensional theory with, let's say, n plus right-moving gapless electron modes and n minus left-moving ones is anomalous, meaning it's not gauge invariant and does not conserve electric charge, unless n plus equals n minus. So one could go through explanations of that in relativistic physics, but in the context of condensed matter, we can see what goes wrong if we simply re-examine this picture. And now we imagine, first of all, starting with a filled Fermi gas, so all the states below the blue line are filled and the others are empty. And now we imagine turning on an electric field that's trying to accelerate all the particles toward greater momentum. So we imagine turning on an electric field that goes to the right, so to speak. So we turn on an electric field with a sign such that the PVT is positive for each electron, so the electrons will all flow to the right in the picture. And that will create electrons at P+, because the particles will all move to the right, and some of the negative energy states will become positive energy filled states. But it will create holes at P-, because the Fermi gas is flowing to the right, and there's a depletion of the states near the Fermi level. So it will create electrons at P+ and holes at P-. So the charge carried by either of the two modes is not conserved, although the total charge is conserved, of course. So relativistically, you analyze more abstractly that the Dirac equation with only one chirality can't be quantized consistently in an electromagnetic field. But here we see rather concretely that charge is conserved, but it's not conserved separately for the right-moving and left-moving modes. So charge conservation depends on having both types of mode equally. Now, there's more we could say in one dimension, but instead we'd better go on to 3 dimensions. So as a preliminary, let's recall that quantum mechanical energy levels repel, which means that if lambda is a parameter and h of lambda is a generic one-parameter family of Hamiltonians, depending on lambda, and with no particular symmetry, then generically, the energy levels do not cross as a function of lambda. The spectrum will look something like that as a function of lambda, and the levels avoid crossing. But how much do levels repel each other? Generically, how many parameters do we have to adjust if we want to make 2 energy levels coincide? Well, the answer to this question is that we have to adjust 3 real parameters generically to make 2 energy levels coincide. And that's because the generic 2x2 Hermitian matrix depends on 4 real parameters, which are A, C, and the real and imaginary parts of B. But if the energy levels are equal, it only depends on 1 real parameter, which is A. So we have to control 3 real parameters to make 2 energy levels cross. To say it differently, any 2x2 Hermitian matrix is a constant plus the sigma matrices dotted with some vector B. And the condition for H to have equal eigenvalues is that B should be 0. And that's 3 real conditions because B has 3 components. So with no particular symmetries, 2 energy levels will cross in 3 dimensions, or as a function of 3 parameters, but not as a function of fewer than 3 parameters. Now, in 3 dimensions, a band Hamiltonian depends on 3 real parameters, namely the 3 components P1, P2, and P3 of the momentum. So it's natural for 2 bands to cross at some isolated value of the momentum, which I've called P star. So near P equals P star, I'm looking only at the 2 bands in question. The Hamiltonian looks something like this. There's some function of P. So P is a vector value quantity. It has the 3 components P1, P2, and P3. The Hamiltonian is a function, a scalar function, plus a vector function dotted with the sigma matrices. And the levels cross at the point where this vector function is 0. Now, if we expand near P equals P star, well, by hypothesis, the 3 components of B are all 0 at P equals P star, but there will be a linear term where B will be some matrix that I've called A times P minus P star plus higher order terms. The matrix is just the matrix of derivatives dBi dPj. Now, generically, the matrix of derivatives is a generic matrix, so its determinant has no reason to vanish. Generically, the determinant is not 0. So, near the point P equals P star, we ignore the higher order terms. And so the band splitting is described near P equals P star. by a Hamiltonian that's linear in P minus P star times sigma matrices. And I've dropped this scalar term A of P because it doesn't affect the band splitting. So this is the Hamiltonian that describes a generic band splitting near P equals P star. Now, apart from the shift that P goes to P minus P star, this is essentially a chiral Dirac Hamiltonian in 3 plus 1 dimensions. So let's just review that fact. So now we write the same massless Dirac equation in 3 plus 1 dimensions as before, except there are 4 gamma matrices. And they still obey Dirac's Clifford algebra. But now there are 4 of them, so they need a 4 by 4 matrix representation. And we again write the Dirac equation in Hamiltonian form, just as Dirac did, by the same steps as before. We multiply by gamma 0 to remove the gamma 0 that multiplies d by dt. Then we multiply it by I, and we move everything else to the right-hand side and call it the Hamiltonian. And now we find that for a massless Dirac equation, the Hamiltonian looks like so. Well, since we now have 4 gamma matrices, to represent them we need 4 by 4 matrices. But an important fact is that the product of all 4 matrices is Lorentz invariant. So one usually multiplies it by a factor of I so that its square is plus 1 instead of minus 1. And it's traditionally called gamma 5 because traditionally the gamma matrices were numbered from 1 to 4. And so 5 came next. But now we've got a little gap. Anyway, gamma 5 squared is 1, so its eigenvalues are plus or minus 1. We can place on psi a chirality condition that gamma 5 psi is plus or minus psi. And then psi would only have 2 components instead of 4. This condition, first of all, is Lorentz invariant. And secondly, it's compatible with the Dirac equation because gamma 5 commutes with this operator here. So it makes sense to write a 2 by 2 Dirac Hamiltonian for an electron that's supposed to have only 2 components, provided it's massless. I'll explain in a moment why the electron has to be massless. But then because of the factor of I in the definition of gamma 5, and in contrast to what happens in 1 plus 1 dimensions, the adjoint of psi, which corresponds, let's say, to the antiparticle relativistically, obeys the opposite chirality condition. So this is in Lorentz invariant or Hamiltonian form, the chiral Dirac equation in 3 plus 1 dimensions. But to express it in a form similarly to what we had when we discussed the band crossing, we have to proceed as follows. Once we impose the condition that gamma 5 psi is psi, the matrices that appear in the Hamiltonian become 2 by 2 matrices because psi only has 2 components. And we can take them up to sign to be the Pauli matrices. The point is that once gamma 5 psi is plus or minus psi, we find that in acting on psi, these matrices do obey the algebra of the Pauli matrices. So the Dirac Hamiltonian for a chiral fermion becomes sigma dot p times the speed of light times plus or minus 1, where the plus or minus 1 corresponds to the fermion chirality. So in writing this formula, I restored the speed of light. As a matter of terminology, a charged Dirac fermion of definite chirality with a definite value of gamma 5 is called a Weyl fermion. The physical meaning of the eigenvalue of gamma 5 is that it determines the fermion helicity. Helicity is defined as the spin along the equation of direction of motion. So a massless fermion is always traveling at the speed of light. So in any Lorentz frame, it has a direction of motion. And it makes sense then to consider the rotation around the direction of motion. And the helicity of the fermion, which for a spin half fermion will be half or minus half, is the spin around the direction of motion. That's a Lorentz invariant notion for a massless fermion. So for a massless fermion, it's possible to have a 2-component fermion